So in this session, we are going to talk about sets, okay? So you already would have studied about sets in probably your junior college or school. So this is not something new to you. We are going to start off with the definition of a set. We define set as a collection of well-defined objects, okay? Collection of well-defined objects. So the key takeaway here is that we are talking about well-defined, okay? I should be able to uniquely determine if an object is part of my set or if it is not, okay? So if I have to take an example, let us say X, okay? I call this, or let us take it as capital X, okay? And let me have this set as collection of all even positive integers. So it is going to have values like this, okay? Something like this. I define it as collection of even positive integers, okay? So when I say it is collection of even positive integers, I am defining it well, okay? I am ensuring that there is no room for any doubt that if I take a number, let's suppose 7, then if it is a part of this set or not, because I say it is even and it is positive. But 7 is odd, therefore I say 7 is not an element of this set. So what is an element of the set? An element of the set is an object contained in the set, okay? So we are just going to look at a terminology over here. Element is a object contained in the set. Okay, so how do I refer an element, or how do I say that an object is an element? I refer it like this. I say 6 is an element, okay? This is used to represent an element. 6 is an element of X, okay? That is how I show that something is an element of X. And if I have to say that 7 is not an element of this set, then I am going to write it as 6 is not an element of X, okay? So let me just write it down for you so that you remember. This implies that 6 is not an element of X, okay? Then another terminology over here that we should remember is known as a null set, okay? So what is a null set? Null set is an empty set, okay? It is a set containing no elements. Set containing no elements. It is represented by the symbol phi, okay? So it is also represented as an empty set, okay? So, or it is an empty set. One thing that we should remember is null set is an element of every set, okay? So I'm just going to write it for you over here, stating that null set is an element of every set. since I say that null set is an element of every possible set, I can say that phi is an element of X. Okay. And what is my X? X, I have defined it over here. So this is my X. Although I have not written phi over here, but as a property, I always say that a null element or a null set is a element of all possible sets. Okay. So that was about the null set. Now we are going to understand how do we define a set. What are the different notations that we have for defining a set? Okay, so I'm going to put down a heading saying that set notations. Okay, in set notations, first method of defining a set is to represent it in a list. Okay, which is written as a listing method of set defining. Okay, so it looks like something like this. You can say that, let us suppose my set is A. Okay, and I can say that A has these many elements. I list down the elements of A. So let us suppose A is 2, 4, 6 and 8. Okay, another way to represent A would be to write it in a statement. Okay, so another notation is the statement form, which I can write like this. I can say that A is equal to set of all positive even integers less than 10. Okay, so this is another way of representing the same set A. Okay, and the final method of representation is known as the set builder notation. Okay, we are going to see that as well. Set builder notation. In a set builder notation, you would represent A something like this. You are going to say that A is equal to X. Okay, where X is positive integer and X is less than 10. Okay, so this is another way known as the set builder notation, where you're representing your elements in terms of X. Okay, you're saying that X is a positive integer. Okay, so X is something like this. Okay, let us call it as positive even integer so that we do not change the definition of this set. X is positive even integer. Okay, so now my X is something like this: 2, 4, 6, 8, 10, 12, 14. And I am also saying that X is less than 10. Therefore, I eliminate the possibility of this. So what I am left with is X equal to this, which is what I wanted. Okay, so this is known as the set builder notation of representing or defining a set. Okay, now let's look at some common sets that we normally use. Okay, so I would just write it as common sets in use. These are the set of all natural numbers. Okay, so it is normally represented with a n, and it is set of all natural numbers. So what does it have? It has something like this. Okay. Another is the set of all integers. Okay. All integers. So it is going to have values like -1, 0, 1, 2 and so on. Okay, in both positive and negative direction. Then we have the set of all positive integers represented by z plus. Okay, set of all positive integers. So it is going to be something like 0, 1, 2 and so on, only in the positive direction. Then we have the set of all rational numbers. Okay, set of all rational numbers. Then we have the set of all positive rational numbers. It is represented by Q plus set of all positive rational numbers. Okay, and similar to the concept of rational numbers, we have set of real numbers. Set of all real numbers and the set of all positive real numbers. Okay, positive real numbers. Okay, so I can use these sets in my set notation. Okay, so what I can do over here is I can also write x is an element of positive integer and x is even. Okay, and x is less than 10. I can do something like this as well to represent my a. So what would my a would be? A is an element of z plus. Okay, so it says a contains values like 0, 1, 2, 3, 4, 5. Then I'm saying x is even. Okay, so x is even, therefore I can eliminate this, I can eliminate this. Okay, I can eliminate this, and it says x is less than 10, so I am left with these values. Okay, if I have to eliminate 0 as well, I'm going to say x is not equal to 0. Okay, or x is greater than 0, right? I can write like this, and x is greater than 0. Then even this goes off, so I'm left with only 2, 4, 6 and 8. Okay, now let us understand the concept of subset and superset. Okay, let me put down a heading saying subset or supersets. So what is a subset? I say that A is a subset of B. A is a subset of B if all elements of A are also elements of B. Okay, so if I have to write it using predicate logic, I am going to say that for all x, okay, if x is a subset of A, okay, then it implies that x is a subset of B as well. Okay, if x is a subset of A, then x is subset of B. Then I can say that A is subset of B. Okay, if X is element of A, then X is element of B, then A is called as subset of B. Okay, this is read as A is subset of B. It is also read as B is a superset of A. Okay, so similar to the concept of subset, you have the concept of superset. So if I have to take an example, what I can do is, let me define A as something like this. Okay, and let me define B as something like this. Okay, now what you can see over here is the elements of A are contained in the set B. Okay, you have 2 over here, you have 2 over here as well, you have 4, you have 4 over here as well, 6 over here as well, a 8, okay, a 10. Okay, so all the elements of A are present in B, therefore I can say that A is subset of B, or B is a superset of A. Okay, but the thing in the concept of subset is, if you have, let's suppose, a set like this, and you have another set which is also 0, 1, 2, 3. Okay, then also you are going to say that C is a subset of D, because 0 is contained in D, okay, 1 is contained in D, 2 is contained in D, and 3 is also contained in D. Okay, so what I can do is, I can say over here that C is subset of D, and I also can say that D is a subset of C, because 0 is contained in C, 1 is contained in C, 2 is contained in C, and 3 is also contained in C. Okay, therefore even this statement is true. And when we have such a scenario, we say that when this is true, we say that C is equal to D. Okay, this is known as set equality. Okay, set equality. So if I have to define set equality, it is going to be two sets are equal if both are subsets of each other. Okay, if both are subsets of each other. Okay, so that was about subsets and set equality. Now I would like to tell you something about what is known as a proper subset. Okay, proper subset. So with proper subset, we eliminate the condition of equality. Okay, how do we do that? We define a proper subset by saying that, let us say A is a proper subset of B. Okay, this is the symbol indicating proper subset. We say A is a proper subset of B if A is a subset of B, okay, and there exists a X, okay, such that X belongs to B and X does not belong to A. Okay, so this is the meaning of proper subset. If I have to write it in English, it's gonna say that if A is a subset of B and there exists an element in B such that it is not present in A. Okay, such that it is not present in A. So if I have to take the same examples over here, let me just copy this, okay, and I'm going to paste it over here. Now I know A is a subset of B, but is A a proper subset of B? Let us check it out. My definition says there should be an element in B such that it is not present in A. Okay, so I can see over here that 5 is present in A. 5 is an element of B, but it is not present in A. Therefore, my condition is fulfilled. I have to look for only one element. There exists, okay, it could be more than one, but if I show that there exists a one element, I am able to prove that it's a proper subset. Okay, therefore I can say that A is a proper subset of B because I have 5 as element of B and 5 is not an element of A. Okay, but in this set C and D, you see that A is not a proper subset of B because there is, or rather C is not a proper subset of D because there is no element in D, okay, which is present in C or vice versa. Okay, because there is no X present in D which is not in C. Okay, similarly there is no X present in C which is not in D. Therefore, I have to say over here that C is not a proper subset of D and D is also not a proper subset of C, although C is a subset of D and D is a subset of C. So that is the concept of proper subset. Okay, now we are going to understand what is a universal set. Okay, universal set. Universal set is defined as a set that is superset of all sets under consideration. Okay, so a set that is superset for all sets under consideration. Okay, a universal set is represented by a big U. Okay, capital U. So if I am looking at sets A and B, okay, let us do that. If I am looking at sets A and B, then the universal set could be over here Z, okay, the set of all integers, because A is a subset of Z, okay, and B is also subset of Z, right? Therefore, I see that Z is superset of both A and B. Therefore, I can call Z a universal set under this scenario. The scenario is I am looking at A and I am looking at B. For some other scenario, a universal set is going to be different. Now we are going to take a look at set operations, okay? All the operations that are allowed in a set and their meaning. So the first operation that we are going to consider is known as the complement operation, okay? So complement of A or for any set is defined as follows. Complement of A written as A bar is equal to all elements which are not in A. Okay, so I'm going to write it like this. X and X is not an element of A. Okay, so if I have to take an example, what I can do is, let us suppose A is 1, 2, 3 and 4, okay? Then the complement of A is going to be, it's going to be all elements which are not in A. So it can have 0, it can have -1, it can have -2, it can have 5, it can have 6 and so on. Okay, it basically depends upon how I am defining my universal set. Okay, so if I define my universal set as the set of integers, then complement of A is going to have these elements. Okay, but if I define my universal set as real integers, okay, then my complement of A is going to be something like 1.1, 1.2, okay, 1.3, 0.1, 0.2, everything. It can have all the real values except for 1, 2, 3 and 4. Okay, so your complement is basically dependent on the universal set. So I'm also going to add over here that the complement of A is X is present in the universal set, okay, and X is not present in A. So that is the meaning of the complement of A. Okay, so you just keep this in mind also. Just remember some common properties over here. The complement of a null element is equal to the universal set, okay, and the complement of the universal set is equal to the null element. Okay, so I'm just going to put this in a box so that you remember. Why is it so? Just look at this definition. The complement of union is, or the complement of universal set is going to be what? X belongs to universal set, okay, and X does not belong to the A, but A is over here the universal set. Therefore, X is the null set, okay, and hence I have this property. Okay, so same way you can prove the other property as well. Okay, now that we have looked at the complement operation, we are going to look at what is a union operation. Union. So the union of two sets represented as A union B, okay, the union of A and B or A union B is defined as all the elements X such that X is an element of A or X is an element of B. Okay, so if I have to write this in simple English, I am simply going to say that union contains all elements contained in either A or B. Okay. So let us take an example. Let me say that my A is equal to 1, 2, 3, 4, 7. Okay. And my B is equal to 2, 3, 7, 9. Okay. And 11. Okay. Then A union B is going to be what? Then A union B is going to be all the elements that are contained in either A or B. Okay. So it is going to have this 1. Okay. It is going to have this 2. It is going to have this 3 also. It is going to have this 4 also. It is going to have this 7 also. Then from the elements of B, 2 is already present, so I am not going to add it. 3 is also already present, so I am not going to add it. 7 is already present, but 9 is not present, so I am going to add it in the union of A, B, and I am going to add 11. So what I am left with is the union of A and B. It contains all the elements which are part of either A or B. Okay. Your union is similar to the concept of OR. Okay. I can also represent a union with the help of a Venn diagram. Okay. A Venn diagram looks something like this. Let us suppose this is my universal set. Okay. And let us suppose this is my A and this is my B. Okay. Let us call this as A. Let us call this as B. And this is my universal set. The rectangle represents the universal set because the universal set is superset of both A and B. Therefore, A and B should be contained within the universal set. Therefore, I see that these two circles which are representing A and B are contained within U. Okay, within the universal set. And if I have to represent a union of A and B, it is represented like this. So it has everything that A has plus it has everything that B has. Okay. So A union B is the shaded region. Okay. It is this shaded region. Right? The same thing you can also use in a complement. Okay. Where did our complement go? Yeah, this is your complement. You can represent a complement in a Venn diagram as well. What you're going to do is, let us draw a universal set. Okay. So let us assume this is my universal set, and in this I have my A. Okay. This is A and this is the universal set. Then the complement of A is represented by this region. What is this region? This is the region which is part of the universal set but not part of A. Similar to our definition of complement of A, which is part of U but not part of A. Okay. So I can write over here the complement of A. Let's use a different color. The complement of A over here is the shaded region as represented by this. Okay. And over here it is this shaded region which is A union B. Now let's look at the next set operation, which is the intersection operation. Okay. I define intersection of two sets, okay, A and B, and I write it as A intersection B as like this. X, where X is a element of A and X is an element of B as well, okay. So if I have to write it in English, I am going to say the intersection is all elements that are part of both A and B, okay, both A and B. So your intersection is basically similar to the concept of AND, okay, and your union is similar to the concept of OR, okay. Just remember this if you have to draw an analogy, okay. So let us take an example. Let us just have this only, okay. I'm going to take the same example and I'm going to show you what is an intersection over here. Okay, so let's make this brace a little better looking. So I have A and B like this. Now I want to find out what is A intersection B. How have I defined A intersection B? I say it contains all elements which are present in both A and B. Okay, so let us find those elements. Is 1 contained in both A and B? No. Is 2 contained in both A and B? Yes. So I have 2 over here. Is 3 contained in both A and B? Yes. What about 4? No. What about 7? Yes. Okay. Therefore, I have the intersection of A and B as 2, 3 and 7. Okay. If I have to represent this in a Venn diagram, I am going to do something like this. I am going to first draw a universal set. Okay. In the universal set, I am going to draw A and I am going to draw B. Okay, so let us suppose this is A and this is B and this is the universal set. Then the intersection of A and B is this particular region, okay, because this region is contained in A and this region is contained in B as well. Therefore, this region represents all the elements which are contained in both A and B. Okay, so this is the Venn diagram representation of intersection. A intersection B represented in this shaded region. Now let's understand one more terminology over here. That is the concept of disjoint sets. Okay. I say that two sets are disjoint if their intersection is an empty set. Okay, if A intersection B is an empty set, then I say A and B are disjoint. Okay, so let us take A as 1, 2, 3. Okay, and let us take B as 4, 5, 6. Then I can see over here that there is no element which is common in both A and B. Therefore, A intersection B is an empty set. Hence, I say A and B are disjoint. Okay, since A intersection B is an empty set, Therefore A and B are disjoint. Okay. Since you do not have an intersection, your Venn diagram is going to look something like this. You are going to have your universal set. Okay, you're going to have a and you're going to have a B. But because there is no overlapping region between them, indicating that there are no elements common between them, I am going to keep the two circles separated. Okay, and this represents what? This represents a disjoint sets. Okay, there is no common area of overlap. Let us call this as A and let us call this as B, and this would be my universal set. Then A and B are disjoint as per this Venn diagram. Okay. Now let's look at some properties of union and intersection. Okay. Properties of union and intersection operations. The properties are: A union with an empty set is equal to A itself. Okay. Then A union with a universal set is equal to universal set. Similarly, A union complement of A is equal to the universal set. Okay. And regarding the intersections, I have A intersection empty set is equal to empty set. Okay. A intersection universal set is equal to A, and A intersection complement of A is an empty set. Okay. How do you know these are true? You can just create a Venn diagram and check for yourself. Okay. For this, let us try to create a Venn diagram. So my Venn diagram is going to be something like this. This is my universal set. Okay. And I have a A over here. Okay. Now I am looking at A union an empty set. Okay. So my empty set is lying outside of this universal set. Okay. So the union is obviously going to be A itself. So it is this region because it is empty set or A, which is equal to A itself. Okay. Now about A union universal set. Let us suppose this is my universal set. Okay. And I have A over here. I am talking about all the elements which are present either in A or in U. Okay. So I am talking about all these elements. Okay. And what is this? This is U. Okay. Same concept I have over here. A union complement of A. Let us see how do we represent it in a Venn diagram. So this is my Venn diagram. Okay. Here I have A. Okay. And everything outside is complement of A. Okay. So just look at this. This is your A, right? And this is your complement of A. Right? This is your complement of A. And you are trying to take a union of both these regions. So what do you get out of it? You get everything. Okay? You get the whole region as the union of A and complement of A, which is nothing but the universal set. Okay? And same concept over here. You are having a universal set. Within this you have A, and what you want is intersection of A and phi. Empty set and A have nothing in common, therefore the answer is going to be phi. Okay, then the next is the intersection of A and the universal set. Okay, the universal set and A obviously have what in common? They have this region in common. Okay, therefore the answer is A, right? And the final is the intersection of A and complement of A. So let us take this. This is your A, right? Let us draw it like this. This is your A, okay, and this is your complement of A. As you can see over here, both these regions have nothing in common. The complement of A is totally outside of A. Therefore, the common region is an empty set because it contains nothing. Okay, so these were your properties of union and intersection, which you can prove with the help of a Venn diagram.